All right. Then we can begin. Good morning, everybody. And it is a good morning, despite what any current events might inform you of. 2 plus 2 is still equal to 4. I checked this morning. Triangles still have 3 sides. Okay, the universe is not broken, and God is still good. So, with that in mind, we will head forward into the future. But first, a review of the past. Yesterday, we dealt with angles inside and outside and all around parallel lines. So go ahead and take out your work from there and compare to my results here. Check how you did. This is absolutely the best time to ask any and all related questions. Number 1 was very straightforward. In fact, I went overboard here because there was so little to do with our shortcut. All the angles they wanted were the acute ones. Otherwise, there are the results for 2 and 3. Here is 4, 5, and 6. 4, definitely we can tell they are parallel. 5, they are not. And 6, from these known conjectures, it cannot be determined because these angles given are with relation to these other lines that they've thrown in there, and they don't tell us directly about L1 and L2. But I've circled this and I want to come back to it in the future because I think that we can actually determine whether they are or are not parallel. We just need some more information. Not to say information about the diagram, but we need to know more facts and conjectures and relationships from geometry. So maybe in a bit we can come back to that one. All right, here then is all of number 7. And I tried to put the measures as close to that as possible. So E is 26 there, and F is the 58. And then finally, numbers 8, x is equal to 80, and 90, x is equal to 20 degrees, and y is 25 degrees. Any questions from yesterday's practice? No? All right. Then, today we get to talk about polygons. So we're finally going to put it back together. Remember, polygons, and we named them, all their shapes. Since we're talking about angles, let's take a look at the angles inside of polygons. And we're going to go through this somewhat methodically. Okay? I want to, if we were all here, I would have had us do more of an exploration, and we'd take out the protractors and measure and test and compare and build up to that. But lacking that, I'm going to put forth somewhat of an argument. I want to make it seem plausible for our results, but I'm not fully going to prove them. Okay? Here's what we already know. We know that a straight line anywhere is effectively an angle of 180 degrees, right? Half of a full rotation. Go from pointing that way to turn all the way around 180 degrees. We also know all those relationships within parallel lines would result in any acute and any obtuse of the angles combining to be supplementary, that is to say 180 degrees. And so we can establish a new name for this relationship. We would call these two angles here the consecutive interior angles, because they're on the same side of the transversal, and they're both inside the parallel lines there. Or CIA for short. You might see that abbreviation. Those will always be supplementary, right? And so let's extend that further. Take that fact and apply it to two sets of parallel lines, which is in effect creating a parallelogram. Right? We talked about definition of parallelogram. Four-sided polygon where both opposite sides are parallel to each other. So if we do that, these top and bottom lines are parallel. So these two angles are supplementary, right? So let's do this guy. That's 180 degrees. And these two, still between the parallel lines, are supplementary, 180 degrees. And you could look at this any direction because we have both sets here. You could say, hey, between these two, well, I could add those two together, or I could add those two together. Any way you slice it, if I add all four of them together, I would end up with what? Go ahead and shout it out. I have the speaker on now. Don't tell me your arithmetic has slipped so far already. 180 plus 180. Add it all together, what do you get? What's that? 360 degrees. Very good. Yeah, we did that same addition back with the circles, right? 360 degrees. We're going to see these numbers a lot, folks. Don't forget them. All right, now, knowing that then all four angles inside the parallelogram will add to 360 degrees. And we could justify that and say, hey, any way I bend those lines, it's still going to be two sets of supplementary angles by the definition of the parallel lines. We could agree on that, right? So in a sense, I could create a full proof argument. I could write that out and say, hey, this has to be the case. And we're going to do one more thing. Because the parallelogram is great, but it doesn't generalize to the other shapes. So instead what I'm going to do is I'm going to slice it in half. I'm going to say, I want half the parallelogram, but I don't want the same half, that is to say, two of those consecutive angles. I'm going to cut it diagonally with this green line here. And it divides it into two triangles. Now, would you reasonably agree with me that if all of the angles in here added to 360 and I took half of that, I still have this angle, I have a portion of this angle, I have a portion of that angle, but altogether, this angle plus this angle has to add back up to the original red line obtuse angle of the parallelogram, right? I didn't take anything away. So it's all still there. So if you added now all 1, 2, 3, 4, 5, 6 of those, you'd still get that 360. But I just want the half of it. So half of 360, we are back again at 180. Is that a reasonable enough assumption that the three angles in that triangle would add to 180?
Yes.
Yeah? Anyone questioning that at this point? Okay. So we actually are going to generalize that result. This brings us to the triangle sum conjecture. It says the sum of the interior angles of any triangle is 180 degrees. Now, at this point, do you believe me? I think it's a fairly good argument here that this guy should be 180 degrees. But is that every triangle? Any triangle? Really? That sounds kind of suspicious there, Mr. Apple. All possible triangles? Well, turns out this is not a foolproof proof for the sum of triangle. We will explore that some more on Friday to justify why we can be safe in saying, yes, absolutely, any triangle, no matter how you draw it, the interior angles will all add up to 180 degrees. Okay? But this is such a big piece of the rest of what we need that we're just going to accept it for now. We'll come back to it later. So we're going to take that fact. The interior angles of any triangle add up to 180 degrees. Okay? You need to know this. This is top-tier knowledge for the SAT and the rest of geometry and everything going forward. Because everything can be represented as triangles. Seriously, literally everything. Okay? Every video game you've ever seen or played on, all of the graphics are actually composed of triangles. Yes, even Minecraft. I know it looks like blocks, but every square is actually two triangles put together. So what does this mean for the rest of the polygons? What is their angle sum? What can we say about them? Well, we already know that a parallelogram, or even a rectangle here, could be divided into two triangles, right? So if you have four sides, the fewest number of triangles you could divide it into would be 2. And then if each triangle is 180 degrees, and you have two of them, 2 times 180 is 360. Now we're just working backwards from what we did before. It's okay. And if it is a regular polygon, that is to say, all of the angles are congruent, you would take your sum and divide by the number of sides, and you would find out that each individual angle would have to be 90 degrees. I'll go ahead and write the equation there. And does this keep working? Can we do that for every shape? Yes, we can. Check out the pentagon. I can draw a diagonal across there, and now I have triangle up top. And now this is 1, 2, 3, 4 sides, so let's draw another diagonal like this. Here's a triangle. Here's a triangle. So if I have 5 sides, I can create 3 triangles. 3 times 180 degrees. Or 180 plus the 360, add the 0, 8, 9, 10, 11, 12, 13, 14, 3, 4, 5. 540? Yeah, there we go. Got it just before I did. 540. And what is 540 divided by 5? 108. 108. Good. See where we're going with this? Now what if it's an irregular shape? This is 1, 2, 3, 4, 5, 6. This is a hexagon. It's not a regular hexagon. In fact, it's not even a convex hexagon. It's concave. Look, it's got that dent in there. Does it still hold up? Can I still divide it into triangles? Give me a straight line, please. I can go there. I can go there. I can go... Technically it works, right? And it doesn't have to be that one. I could go also this way or this way. Right? It does not matter from which corner you pick from. I could even do a combination. Maybe we want to go like that. Zigzag. They don't all have to share the same vertex there. But I still end up with 1, 2, 3, 4 triangles every time. And so then 4 times 180 is aka 2 times 360.
720.
What everybody thought the last axe box was going to be called. 720 degrees. And we could do 720 divided by 6 and get what? $120. So what do you predict? Look at the pattern here. 4 sides, 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. 8 sides, how many triangles?
5.
Say again?
16.
16?
Sorry, oh, yes, sir.
That got a lot bigger real quick. I went from 2 to 3 to 4 to 16? That seems like too many. Try it. Draw one. Draw an octagon. Divide it up into triangles. What do you get?
Could it be 6?
It would be 6, right? Because the general rule is however many sides you have that minus 2 triangles, right? Oops. Everyone here is 2 less. So the sum in an octagon would be 6 times 360.
$2,160.
2,000 how many?
160.
Yeah, 2,160. Oh my goodness. And what is 2,160 divided by 8? $270. Goodness. So the sum will always be 180 times n minus 2. Put a box around that. And then the measurement will be that divided by n. Put a box around that one. Those are good formulas to know. They can save you a lot of time. But if you don't remember those formulas, you could work them out yourself. Just remember, always divide every shape into triangles. Every triangle contains 180 degrees. And you can work from there. Any questions so far? Right, that's interior angles. That'll let you figure out what's inside the shape. What about on the outside? The exterior angles. Take a look at this guy. Here I have a 1, 2, 3, 4, 5 pentagon drawn in, but I've extended the lines. Right? It's more than just the bare minimum segments to create the pentagon. Okay? And I want you to imagine, well, before we get to that, let's quick identify here. Interior versus exterior. Okay? This angle is outside the pentagon. This angle is inside the pentagon, right? In fact, let me switch to highlighter here. Right? All of these are exterior, and the red ones are interior. You agree? We're quite literally talking about drawing inside and coloring inside the lines. We've done that since kindergarten. Okay? So now, what do you think would happen if I was to add up all of the exterior angles? Just like we did with the interior angles. We found, okay, if I added all the interior angles, I would get a number. What about if I add up all the exterior angles? There's a lot of exterior angles. There's a lot of options here. Look at this side. I extended both sides of the polygon, and I got 1, 2, 3 angles here. I only extended one side over here, and I just got that one exterior angle. Although really we could count this as a straight angle. Is that another 180 degrees as well? Oh, geez. There's a lot to consider there, right? So when we're talking about exterior angles, we are talking about only the clockwise or the counterclockwise, not both at the same time. So imagine this. You start down here. Outside, on the block, you're just going to go for a walk. And you head down the sidewalk. And you get to the next street. And this street is going at kind of an angle here, and you've got your choice. Okay, you're going to turn left, turn right, go straight. You make a turn. In this case, we're turning to the right. And you continue down the next street. And you've established you're turning right. So you're going to make the same turn every time. This is the direction I was going in. That's the arrow pointing there. And when I get to the end of the block, I'm going to turn in the same direction. Turn, in this case, clockwise, going around the face of a clock. You've got to have an analog clock for this to make sense. Right? And so now I'm going in this direction. But when I get here, I'm going to turn the same way. So that angle, that exterior angle now, is how much I had to turn at each intersection, right? And then you keep doing that. You come down here, turn again, come back here, and now you're back to where you started. Most blocks, I know, city blocks tend to be more square, rectangular. Here's a pentagonal block, just to throw things off, because it doesn't matter what shape it is. If I added all of those turns that I took, this one, and this one, and this one, and this one, add those turns together, how many degrees will I end up with to get back to where I started? Notice I'm including this one. So I'm including starting facing this direction. If you face this direction And it doesn't matter how far you walk. We're just talking about the turns. I turned this way, and then I turned this way, and then I turned this way, and then I turned this way. How much turning did I do to face back to the way I started? That's a full circle, right? 360 degrees. Look at this another way. I love this picture from the book. Here's a similar diagram. Pentagon again. Doesn't have to be. But they've extended the rays on one side. And what they're doing with this is they are shrinking that pentagon, but keeping those extended sides still there. So as the pentagon shrinks and shrinks and shrinks and gets tinier and tinier, notice it all converges down until it's just a single point. And then the only thing left we have is those exterior angles. One here, and here, and here, and here, 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 here. I've just drawn a whole circle, haven't I? So no matter the size, no matter if it's regular or irregular, the sum of the exterior angles on any polygon will always be 360 degrees. That's pretty nifty. Especially when you compare it to before. The interior angles, well, their sums got bigger and bigger and bigger. Right? And the individual angles got bigger and bigger and bigger. The exterior always stays the same, always 360. Stuff to think about. All right. So with that information, you should now be armed and ready to tackle these exercises for today. Finding all the angle measures in these kinds of diagrams. Look at these fun shapes we got going on. Right? This guy, look, 1, 2, 3, 4, 5. Here's a pentagon. Here's a triangle attached to it. Oh, notice it's got some markings here. This is an isosceles triangle. All right? It's got some symmetry going on. Don't forget about that. And same thing down here. You've got a triangle and a square and a pentagon, all regular. Those extra markings. This is a really fun one, right? Remember, just like when we shrunk the shape down all the way to a single point, the angles all the way around one point must be equivalent to a circle. This all the way around is 360. So when you know this guy and this guy and this guy, you can subtract them all from 360 to find A. A lot of people forget that one. All right? Some of these bits are pretty easy. Some of these bits are challenging. Let me know if you have any questions, but otherwise, I'm going to leave the rest to you. We have 25, 15, 16, 17 minutes or so to work. Have at it. Lewis, to answer your question, neither at this point. I'm mostly sticking with my PS4 and PC for now. But we'll see. Depends on which one has the next Batman game.